Okay, so this is the final talk of this session and I guess of the workshop. So, Joongwon.
Yeah. Hello, I'm Joongwon Ahn from Seoul National University. Today I'm going to present retargeting and abstract interpreter for a new language by partial evaluation. I'm working on this work with my advisor Kwangkeun Yi and my colleague Jay Lee. Abstract interpretation, static analysis is a very powerful technique. However, it is limited to a small set of languages. It is because building an analyzer is an expensive task. And our goal is to reduce the cost by reusing what we already have. Specifically, we are trying to build a static analyzer for T using a concrete interpreter for T written in S and an abstract interpreter for S. Here, T stands for target and S stands for source language. Key idea is to use partial evaluation. Consider the situation where we partially evaluate the interpreter for S with respect to an interpreter for T, which is written in S. The result is another interpreter for T, which is written in a language that was used for writing the S interpreter. This can be extended to abstract interpreter. So we can specialize an abstract interpreter for S with respect to a concrete interpreter for T. And the result would be some kind of interpreter for T. So natural question is this a sound abstract interpreter? And the answer is yes. Partially evaluating a sound S abstract interpreter produces a sound T abstract interpreter. The proof directly follows from the correctness of two interpreters and partial evaluation. The equality on the left is just a correctness condition for the concrete interpreter, and the membership sign in the middle is a soundness condition of the abstract interpreter. And the last equal sign is just describes what the resulting program, the result program of the partial evaluation behaves. Now the more interesting question would be, how does the resulting abstract interpreter look like? I'm going to demonstrate it using small languages. Here we use an imperative language with fixed size memory for S, and for T we use very tiny assembly-like language with single register and two instruction, which is addition and multiplication. The first ingredient is a T interpreter, which is written in S. The implementation is straightforward. It just fetches the instruction that is pointed by program counter, and according to the instruction, we update the value of the register. And then we advances the program counter. For example, if we are trying to evaluate the program S3 mode 2 with input 42, we run this interpreter with initial S memory, where the first cell stores the register value and the second cell stores the program counter. After two iterations, we get the final register value in the first cell of the memory. The second ingredient is an abstract interpreter for S. We wrote a standard abstract definitional interpreter where the evaluation of the expression is done by recursion with abstract operators, and the evaluation of statements is done by open recursive function, where the control flow is handled by abstract filters and joins. Now that we have two ingredients, we can do partial evaluation. Since the resulting program is a bit verbose, we only include a small portion of the program. Now I'm going to focus on two aspects of this resulting abstract interpreter. The first point is that the abstract operators that were used in S analysis is being reused in the resulting T analyzer. This means that the abstract domain that were designed for S analysis is directly used in the T analysis. And the second point we can observe is that the structure of the interpreter is reflected in the resulting abstract interpreter. For example, the while loop in the concrete interpreter is reflected as a recursive call at the last line, and the case analysis on instruction is reflected as joins of 3 abstract states, where each abstract state represents each case of instruction. So the next question will be, how general is this approach? This motivates 2 directions in future work. The first one is to apply this approach to more realistic settings. For S language, we plan to add more rich features such as functions, heaps, and algebraic data types, which is commonly used for writing interpreters. And for T language, we are trying to apply to more realistic language that resembles JavaScript or Python. And we are also interested in domain-specific languages. These languages are used widely in practice, but they often lack the static analyzer because building dedicated static analyzer for these languages is too expensive. We hope this approach will be particularly helpful for those cases. And the second direction is to study relations between the precisions of S and T analyzers. For example, in our demo, the concrete interpreter used the second cell of the S memory as the program counter for T programs. Therefore, if we want T analyzer to be flow sensitive, the input S analyzer should be sensitive on second memory cell. This is quite arbitrary, so we are investigating to generalize this relation and find a systematic way to derive the necessary S sensitivities for desired T sensitivities. To conclude, partial evaluation can be used for retargeting abstract interpreters. Thank you for your attention.
Talks are getting shorter and shorter. Thanks for a nice talk. Do we have questions? No questions? I guess I have a question.
Yeah.
You were composing 2 different interpreters together. Have you thought about having a whole stack of interpreters?
That will be interesting direction, but partially evaluating a single abstract interpreter is still very difficult. So we are first investigating the case involving only 2 interpreters.
That seems very sensible. Any more questions? Nope. Okay, well, let's thank our speaker again.